Bismillahirrahmanirrahim. We continue our discussion on number system, and in today's discussion we will be performing hexadecimal conversions in rest of the other number systems. So far we have studied different number system conversions that include 3 conversions for decimal number system, such as decimal to binary conversion, decimal to octal conversion, and decimal to hexadecimal conversion. That makes a total of 3 conversions for decimal number system. Then we performed 3 conversions for binary number system that include binary to decimal number system conversion, binary to octal conversion, and binary to hexadecimal conversion, collectively making 3 conversions for binary number system. Then we also have completed 3 conversions for octal number system that include octal to decimal conversion, octal to binary conversion, and octal to hexadecimal conversion, a collective of 3 conversions for octal number system. So a total of 9 conversions have been completed, and in previous lecture we were discussing hexadecimal conversions, and we have completed one of its conversion, that is hexadecimal to decimal conversion. So a total of 10 conversions have been completed so far, and we had said that there are a total of 12 conversions. Since 4 number systems are there, and every respective number system is converted to 3 other number systems, so a collective of 12 number systems are there. In today's discussion we are discussing hexadecimal conversion, and we will be talking on how we can convert hexadecimal number to binary number system. Let's proceed with our today's discussion. We are discussing number system conversions. As I just said, we have already completed 10 number system conversions, and we are discussing hexadecimal conversions. In today's discussion, we will be discussing hexadecimal to binary number system conversion. Let's see what is the mechanism, what are the methods that we can use to convert a hexadecimal number to a binary number system. We have already performed binary to hexadecimal conversion in previous lectures, and today we will be discussing its reverse, how we can convert a hexadecimal number to a binary number. As you all know, hexadecimal number system consists of total 16 symbols that include 10 digits from 0 to 9, and rest of the 6 symbols have been taken from 6 alphabets. That means A represents alphabet A represents digit 10, B represents 11, C represents 12, D represents 13, E represents 14, and F represents 15. So a total of 16 symbols that include both digits and alphabets are collectively formed to make a hexadecimal number. Hexadecimal number is commonly used to represent memory addresses in modern computers. Previously, they were used to represent by using octal numbers, but in latest computers, hexadecimal has replaced octal numbers to represent the memory addresses. Binary number, on the other hand, consists of just two numbers, 0 and 1. And it is also known as computer's native language. Computer only understands binary numbers. So whatever is entered in computer is ultimately converted to binary number system. So in today's discussion, we are going to convert a hexadecimal number to binary number. What is the technique that we can use to perform this type of conversion? The method is, we have to split every hexadecimal number. Every given digit within the hexadecimal number is split in group of 4 binary digits. And how you can split it? Every digit must start with power of 2. The power of 2 starts from 0, and this conversion process moves from right to left. So we split every digit within the given hexadecimal number in group of 4 binary digits. How we can do it? You need to write every digit within the hexadecimal number in 2 powers. Power of 2s, you can say. The power of 2 would start from 0, and this conversion will move from right to left. In next step, we need to keep the binary digit that is required to generate the given hexadecimal number as on. That means you have to keep that number as 1, and the remaining of the numbers within the 4 binary digit group will remain off. That will ultimately generate a binary number. And at the end, we will group all the generated binary numbers. That will be a collection of zeros and ones, and that would be the required answer. So let's see how we can apply this method on some examples. Let's see, we are given a hexadecimal number. Here you can see 4FA, and we need to convert it to binary number. The method, as I just described, says we need to split every digit within the given hexadecimal number in group of 4 binary digits. So here you can see 4 hexadecimal numbers are given, 4FA. 3 hexadecimal numbers are given here. So we need to split every single hexadecimal digit into group of 4 binary digits. How we can do it? Let's see. Then the given hexadecimal number is 4FA. So we need to split every individual hexadecimal number in this way. 4 will be split in respective 4 binary digits, F will be split in 4 binary digits, and A will be split in 4 binary digits. As you know, F represents digit 15 and A represents digit 10. So how we can split them? This is how we convert every digit in group of 4 binary digits. So the splitting process says power of 2's are written in 4 groups. Starting, the power of 2 starts from 0. The conversion process moves from right to left. As you can see here, we are moving from right to left. So every respective digit within the hexadecimal number is split in 4 binary digits in this way. Now, as you can see, 2 raised to power 0 shows 1. 2 raised to power 1 shows 2, 2 raised to power 2 shows 4, and 2 raised to power 3 shows 8. Now, we need to keep those digits as on. That ultimately would generate 4, while remaining of these digits, binary digits, will be kept as off. So you can see this is 4, so we need to switch on the third bit only, while remaining of the 3 bits will be kept as 0. Similarly, if you need to generate 15 out of these 4 binary bits, so how you can convert this into 15? If you keep all the 4 bits as on means you keep all 4 bits as 1. So that would, if you add up all the 4 bits, 8 plus 4 plus 2 plus 1, that would generate 15. So all the 4 bits required to be switched on. And similarly, if you need to generate 10, how you can do it? Which numbers are to be added together to generate 10? So if we switch on the 4th bit and the 2nd bit, while remaining needs to be off. So this will ultimately generate what? Number 10. 8 plus 2 will generate 10. So this is how we do it. You can see we have switched on those bits that are required to generate the given number, while rest of the bits are kept off in all the 3 cases. Now we merge together all the numbers, all the bits, binary numbers, and collectively they form a binary number. So here you can see 4FA in base 16 is equal to this. We will start from the left side. 4 is equal to 0, 1, 00. But since this starting 0 has no value, or it does not affect the final result, so we do not write the first 0 here, and rest of 1, 0, 0, these bits are written here. Then F is equal to 4 ones. 4 ones, 1, 1, 1, 1 from till here. And 1011 is the conversion for 10. It is written 1010 here. Don't forget to write the base. So this is how we can convert a hexadecimal number to a binary number. Let's see another example. We are given hexadecimal number 9DB2 and we have to convert it into binary number. The method states every individual number within the given binary number needs to be split in group of 4 binary digits. So how we can do it? This is the given number 9DB2. So we have to split this number like this. So 9 will be split in group of 4 binary digits, D will be split in group of 4 binary digits, B will be split in group of 4 binary digits, and 2 will be split in group of 4 binary digits. Here you can see D represents number 13 and B represents number 11. So how we can do it? We have split every individual number within the given hexadecimal number in group of 4 binary digits. How you can convert the group of 4 binary digits? You need to simply write powers of 2 in 4 groups or 4 times. The power of 2 for first base will be 0, for second will be 1, for third will be 2, and for last will be 3. So a group of 4 binary digits is formed for every individual given hexadecimal number. So now we need to generate 9 out of these given 4 bits. So we need to first, for your simplicity, you can write 2 raised to power 3 means 8, 2 raised to power 2 means 4, 2 raised to power 1 means 1, and 2 raised to power 0 means 1. This is for your simplicity, so you can better add the required numbers to form the given hexadecimal number. Now we need to add those numbers out of these given 4 bits that would ultimately generate 9. So here you can see if you add 8 with 1, this would ultimately generate 9. So we need to only switch on the first and last bit. and keep the remaining of the 2 bits as off. So this would ultimately generate 9. Similarly, if you are to generate 13, so how we can generate? If you add 8 plus 4 plus 1, this would generate 13. So how you can do it? We need to switch on the first, third and last bit, while the second bit needs to be kept off. Similarly, if you are to generate 11, so how you can do it? If you switch on, or if you add 8 with 2 with 1, so this will generate 11. That means if we switch on first 2 bits and the last bit, while the third bit is kept off, this would generate 11. Similarly, if you have to generate 2, so 2 means the only second bit is kept on while rest of the 3 bits are kept off. This will generate 2. So this is how we have done it. We have converted the individual hexadecimal number into a group of 4 binary bits. So some bits are on and some bits are off. After combining all these, the given answer is 9DB2 in base 16 is equal to. We have to first write the bits for 9. 9 is 1001. And then you have to write the conversion for D, which is 1101. And then you have to write the conversion for B, which is 1011. And then you have to write the conversion for 2, which is 0010 in base 2. I hope the method is now clear to you. Now let's see how we can convert the fractional numbers. If you are given a hexadecimal number having a fractional part, so how you can convert it into binary fraction that would again be having a fraction part. So the method says we need to repeat the same procedure as we have just performed for the whole numbers. How we can do it? Let's see with some examples. Here you can see we are given a hexadecimal number 0.10 and we have to convert it into binary number. The method, as it states, split every given digit within the hexadecimal number in group of 4 binary digits. If you remember, in first lecture of the number system, I have mentioned the conversion or the relationship charts between the 4 number systems. So you could see there, or you could consult the first lecture on number system. I had mentioned every hexadecimal number is equivalent to 4 binary digits, while every octal number is equivalent to 3 binary digits. So this is the reason we split every digit in given hexadecimal number in group of 4 binary digits. You can consult the first lecture on number system. So we have to split, this is the given number 0.10, we have to split every number in this hexadecimal number and convert every digit in group of 4 binary digits. So this is the given number, we have split them 0.10 and every respective number has to be converted into group of 4 binary digits. So this is how you can do it. Now after conversion, 2 raised to power 3 means 8, 2 raised to power 2 means 4, 2 raised to power 1 means 2 and 2 raised to power 0 means 1. So which number requires to be switched on in order to generate 0? That means no number requires to be switched on to generate 0. So every number will be kept off. So 4 zeros or simply single 0 is enough to mention it. Decimal point stays at its place. Do not change the position of decimal point. So decimal point will remain here as well. Now, which numbers would require to generate 1? So that binary digit will be on while rest of the numbers will be switched off. So here you can see only the first digit is enough to generate 1. So first digit will remain on while rest of the 3 will be off. Similarly, again there is 0. So which number requires to remain on to generate 0? No number is required to remain on. So all the 4 binary digits must be switched off. You can add single 0 or you can add 4 zeros, but 4 zeros towards the right of the decimal point is important to mention, while towards the left of the decimal point you can only write single 0. No need to write 4 zeros. So this is how the answer is. You can see we have generated the required binary numbers, and after merging them we can write 0.10 in base 16 is equal to, here you can see towards the left of the decimal point there are 4 zeros, but we have written just 1 0 as 4 zeros and single 0 towards the left of the decimal point would result the same. No need to write the 4 zeros. If you do it, again it will not change the answer, but it's better to write a single 0. And then there are the conversion for digit 1, and it is 3 zeros with 1. Here you can see 3 zeros with 1, and then the conversion for 0 again. So again there are 4 zeros, but the zeros towards the right side of the decimal point are required to be written. So we have written 4 zeros here, you can see, and with the base 2. So same procedure we followed for the whole numbers. You have to follow the same procedure for the fractional part. Let's see another example. Again here you can see we are given a fractional hexadecimal number point B1, and we have to convert it into binary number. So how you can do it? Split every digit within the hexadecimal number. So first we have to write it separately. 0.B1. B is equal to number 11. And now we have to split every given number into group of 4 binary digits. This is how we do it. And for your simplicity, you can write 2 raised to power 3 is 8, 2 raised to power 2 is 4, 2 raised to power 1 is 2, and 2 raised to power 0 is 1 for all the 3 groups. Now you have to see which bits are required to merge together or to add together or to remain on in order to generate the given hexadecimal number. So in order to generate 0, we do not need to keep on any of the 4 bits. So all the 4 bits are kept off. You can write single 0 or you can add 4 zeros. You can see here the decimal point stays at its place, so do not need to change or do not try to change the position of the decimal point. Next number, hexadecimal number, is 11. So which bits are added together or remain to switch on in order to generate number 11? So you can see if we add 8, 2 and 1, so it will generate 11. That means first, second and last bits are kept on and the third bit is kept off in order to generate number 11. And similarly, the last number, hexadecimal number, is 1. So how we can generate 1? Only first bit is required to switch on while rest of the 3 are switched off in order to generate 1. Now we merge. This is the answer how we generated them. Merge all the answers, all the bits. So 0.B1 in base 16 is equal to, you can see towards the left of the decimal point only single 0 is enough. So instead of writing 4 zeros, we have to write, or we can write, single 0. But towards the right of the decimal point, all the zeros have significant value, so you have to write all the zeros. So 11 is 1011. Here you can see 1011 is 11 and 1 is 0001. 3 zeros and 1, 3 zeros and 1, and with base 2. So this is how we convert fractions, hexadecimal fractions, to binary fractions. Same procedure you followed for the whole numbers. Now let's merge the decimal part or the integer part and the fractional part and see how we can convert a given complete hexadecimal number having both the integer part and the fractional part to a complete binary number that will again be having an integer part and a fractional part. So the given hexadecimal number is CBA.FF and we have to convert it into binary number. The method, as it is clear to you now, every individual number within the given hexadecimal number is first split into group of 4 binary digits. So we need to first write it individually. CBA.FF is the given number and we have to first split them in this way, as we have to treat every digit separately. So C is actually equal to 12, B is equal to 11, A is equal to number 10, F is equal to number 15, and again F is equal to number 15. Every individual number is now treated separately. So every individual number is split in group of 4 binary digits. How we can group it? We start writing powers of 2. The powers of 2 start from 0. A group of 4 powers will be required to be written, and the placement of decimal point is at its place. Do not change the position of the decimal point. Then for your simplicity, what we have done, 2 raised to power 3 is equal to 8, 2 raised to power 2 is equal to 4, 2 raised to power 1 is equal to 2, and 2 raised to power 0 is equal to 1. We have written it for all the numbers, so you can better understand how we can generate the required number that would give you the placement of zeros and ones. So now let's see which numbers are required to be added together to generate 12. That means those bits must be switched on while rest of the bits will be switched off. So how we can generate 12? If we add 8 with 4, that would generate 12. That means third and fourth bits are switched on. Switched on means they are written as 1 while first 2 bits are written as zeros. We only need 8 and 4 to generate 12. 8 plus 4 is 12. So last 2 bits are required to only switched on while first 2 are switched off. Next we have to generate number 11. So which are the bits that are, if added together, that will generate number 11? So here you can see if we add 8 with 2 with 1, it will generate 11. So that means we need to only switch on or write ones for first and second and fourth bit, while third bit is kept as 0. This will generate 11. And similarly, if we have to generate 10, which bits can be added together to generate 10? That means if we have to add 8 with 2, this will ultimately generate number 10. That means bit second and fourth are kept as 1 while first and third is kept as 0 in order to generate number 10. Decimal point is at its place. Do not change the position of decimal point. Now you have to generate number 15. So which bits are added together in order to generate 15? Those bits will be then switched on while others will be then switched off. But here you can see if we add 8 with 4, that will equal to 12. Then 12 with 2, 13 and 14, and then with last that will be 15. That means all the 4 bits are required to remain switched on. Similarly 15 here. So all the 4 bits are required to be switched on in order to generate number 15. So this is the sequence. Here you can see. This is the generated sequence for the given individual hexadecimal number in the given hexadecimal number complete number. Both the integer part have been converted and the fractional part have been converted. Now we have to merge the answer. The given hexadecimal number is CBA.FF and it has been converted to this. C is 12. It has been replaced with 1100. Here you can see 1100. Next number is a B, which is 11. It is equal to 1011. So here you can see 1011. And then third number was A is 10, which is equal to 1011. So here you can see 1011. And then the decimal point at its place, we have not changed the position of the decimal point. Then if 15 is 4 ones, 15 is 4 ones here, and then 15 again 4 ones, and the last ones here you can see again 4 ones with base 2. So this is how you can convert a complete hexadecimal number having an integer part and a fractional part in a complete binary number that would also contain an integer part and a fractional part. Let's see another example so you can have a better idea how you can handle a hexadecimal number. Here we are given a hexadecimal number 333.E38 and we have to convert it into binary number. So first we have to write every number separately like this. We have written every number separately. Also we have to convert or we have to write the equivalent of alphabets such as E is equal to 14. This is for your convenience so you can better generate its 4 binary bits. Now we have to generate binary bits for group of 4 binary bits for every individual number within the given binary hexadecimal number system. The position of decimal points is at its place. We have not changed the position or location of the decimal point. So every bit, every number within the given hexadecimal number is split in group of 4 binary digits. Now their conversion, 2 raised to power 3 is equal to 8, 2 raised to power 2 is equal to 4, 2 raised to power 2 is equal to 1, 2 raised to power 0 is equal to 1. This is for your convenience. If you do not want to write this step, you can skip it. But this is for your convenience so you can better understand which of the numbers can be added together to generate the required hexadecimal number. So those numbers will be switched on while remaining will be switched off. So now we have to generate number 3. Which numbers are added together here in order to generate 3? So you can see if 2 is added with 1, this would generate 3. That means first 2 bits are written as 1 while third and fourth bit are written as 0. Similarly, 3 here, first 2 bits are on while the third and last bit is switched off. Similarly, 3 again, first and second bits is written as on while 2 last are written as off. Again 3, first and second is on while 2 last are switched off. The position of the decimal remains as its place. Now is digit 14, number 14. So here you can see if we add 8 with 4 with 2, so this will generate 14. So that means if we switch on the last 3 bits and switching off the first bit would generate 14. Similarly, next number is 3. So switching on the first 2 bits and switching off the last 2 would generate 3. And the last number is 8. So how you can generate 8? The only fourth bit is enough to generate 8. So we would keep it as 1 while the first 3 bits are kept as 0. So this is how we converted the given hexadecimal number to its equivalent binary number. After merging up the answer is 3333.E38 in base 16 is equal to this. First 3 is 0011. So first 3 is here you can see I have skipped. You can write these two zeros towards the left of the decimal point, but they are least significant, so you can skip them. So I have just written 1 1 instead, but if you wish you can write 2 zeros here, but they are not required. 1 1 is enough, as towards the left side, towards the left means you cannot skip these zeros. You cannot skip these zeros as they are in between the ones, but towards the left of the decimal point are the least significant zeros, which are also towards the left of ones. You can skip them. So 0 0 1 1, or you can simply write 1 1 for 3. Another, you can see 3 is again there. Now you cannot skip the zeros with it. So 0 0 1 1 is here. Again 3 is 0 0 1 1 here. Again 3 is 0 0 1 1 here. You can see we have only skipped the last two zeros of the last three. Remaining zeros of the remaining of the threes are written. Then the position of decimal point is at its place. Here you can see. Next, towards the right, if we see, the first number is number E, which is 14, and it is converted as 1110 here. Then is number 3, 0011, again 0011, and the last number is 8, which is 1 with 3 zeros. 1 with 3 zeros. You can see here I've written the complete 3 zeros here. Towards the right side of the decimal point, you cannot skip the last zeros even. Towards the left side of the decimal point, the last zeros which do not have further ones towards their left, so you can skip those zeros. We have written the base with the converted number, which is base 2. Do not forget to write the base. As you know, 0 and 1 is also part of decimal number system. It is also part of octal number system. It is also part of binary number system, and it is also part of hexadecimal number system. So you need to mention which type of number system you have converted it in. This is your assignment. You have to convert the given hexadecimal numbers into their respective binary numbers. I have clarified the complete method with different examples, and I hope the method must be now easy for you to attempt this assignment. Assignment will be soon uploaded on KCMS. You need to attempt the assignment within due date and upload it on KCMS. That is all for the hexadecimal to binary conversion. I would like to recap again. We have converted so far a total of 11 number system conversions. 3 conversions for decimal number system, 3 conversions for binary number system, 3 conversions for octal number system, and 2 conversions so far for hexadecimal number system. So a collective of 11 out of 12 conversions have already been completed. We will be performing the last conversion for hexadecimal number system, that is hexadecimal to octal number system, in the coming lecture. So this would complete our 12 number system conversions. That is all for now. I thank you all.